Okay, we continue to learn Chapter 3, Vector Spaces. And Section 3, Linear Independence. This is very important concept in linear algebra for linear independence. Okay, first we say minimal spanning set. Okay, a vector space can be generated by many spanning sets using addition and scalar multiplication. As we see the example before, right? For R3, you can find many spanning set of it. It is desirable to find a minimal spanning set in which there's no unnecessary vectors. So we find those which are really necessary. Okay, unnecessary vectors are those who linearly depend on other vectors, can be represented as a linear combination of other vectors. Need the concepts of linear dependence and linear independence to find which are unnecessary vectors. Okay, consider the following vectors in R3. So x1 here, 1 minus 1, 2. x2 is minus 2, 3, 1. And x3 is minus 1, 3, 8. And then we let S be the span of these three given vectors. So any linear combination of x1, x2, x3 can be reduced to a linear combination of x1, x2. Because x3 equals 3x1 plus 2x2. See? This vector, x3, can be written as a special linear combination of x1 and x2 equals 3 times x1 plus 2 times x2. And then if you write the linear combination of x1, x2, x3 here, then because x3 can be replaced by linear combination of x1 and x2, so we substitute here in here, and you will get this one equals alpha 1 plus 3 alpha 3 times x1 plus alpha 2 plus 2 alpha 3 x2. So any vector which is written by linear combination of these three given vectors can be just written as linear combination of these two vectors, x1 and x2. So this means S equals span of x1, x2, x3 can be just written as span of x1 and x2. So here you can see x3 is unnecessary, right? And similarly, since x1 can also be written as linear combination of x2 and x3, and also x2 can be written as linear combination of x1 and x3. So you can find this span of x1, x2, x3 equals span of x1, x2, also equals span of x1, x3 equals span of x2, x3. So the three vectors, you can choose arbitrary one as an unnecessary vector here. Okay, now we consider the dependency relationship between x1 and x2. If we have two vectors, then we consider if there were scalars c1 and c2, not both 0, such that c1 x1 plus c2 x2 equals 0. So if c1 does not equal to 0, you can have x1 equals minus c2 divided by c1 times x2. Or if c2 does not equal to 0, you can write x2 equals minus c1 divided by c2 times x1. So if neither of the two vectors is a multiple of the other, then the only way this equation holds, c1 x1 plus c2 x2 equals 0, is if c1 equals c2 equals 0. Right? So if we consider the relation between x1 and x2, we consider this linear combination of x1 and x2. And then we consider this homogeneous linear system. Okay, if there's a solution, non-trivial solution, then this means x1 and x2, we can write in this way such that one is a multiple of another. Okay? Otherwise, you will not find a non-trivial solution. And then this equation holds, this homogeneous linear system holds if and only if C1 equals C2 equals 0. Okay, so there are two different cases. Okay, now we have this observation 1. If V1, V2 till Vn span a vector space V, and one of these vectors can be written as a linear combination of the other n minus 1 vectors, then those n minus 1 vectors span V. This means the vector, the one that can be written by others, is unnecessary for the spanning set. Okay. We see the proof here. Suppose that Vn can be written as a linear combination of the other n minus 1 vectors. Then we have Vn can be written as a scalar beta 1 times the vector V1 plus scalar beta 2 times the vector V2 plus Tl plus the scalar beta n minus 1 times the vector Vn minus 1. Let V be any vector in the space V. Since V is a span of V1 till Vn, we can write V as a linear combination of these given n vectors. So we have V equals alpha 1 V1 plus alpha 2 V2 plus Tl plus alpha n minus 1 Vn minus 1 plus alpha n Vn. And we substitute Vn by this equation. We have Vn equals beta 1 V1 plus beta 2 V2 plus Tl plus beta n minus 1 Vn minus 1. So this one can be written as this form. If we write in this form, we know that V can be written as a linear combination of V1, V2 till Vn minus 1 only. Okay, thus any vector in V can be written as a linear combination of these n minus 1 vectors. That is, V equals the span of V1 till Vn minus 1. Okay, now we consider observation 2. Given n vectors V1, V2 till Vn, it is possible to write one of the vectors as a linear combination of the other n minus 1 vectors if and only if there exists scalars C1, C2 till Cn not all 0 such that this equation holds. This is C1 times V1 plus C2 times the vector V2 plus Tl plus the scalar Cn times the vector Vn equals 0. And here, this means this homogeneous linear system has a non-trivial solution. See, if there exists non-zero scale, not all zero scalars here. And we can show in these two directions. This one. Suppose that Vn can be written as a linear combination of V1, V2 till Vn minus 1. Then we want to show that this homogeneous linear system has a non-trivial solution. Okay. Because Vn can be written in this form equals alpha 1 V1 plus alpha 2 V2 plus Tl plus alpha n minus 1 Vn minus 1. We move Vn to the right, and we have alpha 1 V1 plus alpha 2 V2 plus Tl plus alpha n minus 1 Vn minus 1 minus Vn equals 0. And we can set a Ci just equals alpha I for I varies from 1 to till n minus 1, and Cn just equals minus 1. See? So this homogeneous linear system has this non-trivial solution. See? Because Cn is minus 1, not 0. Okay, and from the opposite direction, if there exists C1, C2 till Cn not all 0, Cn does not equal to 0, such this homogeneous linear system holds. This means this homogeneous linear system has a non-trivial solution. Because Cn does not equal to 0, of course, we can write Vn as a linear combination of the other n minus 1 vectors. So we prove this observation.